All right. The next thing we are going to look at is factors influencing chemical shifts. We have anisotropic effect. Now, the chemical shift position for protons attached to carbon-carbon in alkene is higher than could be accounted for by electronegativity effect alone. Now, for instance, if you look at aldehyde and alkene is something like this, right? Good. Now, they have approximate chemical shift value of 4 to 8 ppm. Now, if you look at aldehyde group, of course, you all know what aldehyde group is. The approximate chemical shift value is around 9.5 to 10.0. And then we have that of this. The approximate chemical shift value is 6 to 9. And then we have that of ethyne. The approximate chemical shift value is 1.5 to 3.5. Now, electronegativity alone could not actually account for especially these ones because the values are unreasonably high. We've actually talked about how electronegativity is responsible for the chemical shift value for the halogen compounds, right? And some other compounds, right? The alkyl halides. But when we come here, this could not actually explain electronegativity alone cannot explain. Now, in this case, if you look at it also, that alkyl nucleus have a low chemical shift value. That means there is something. So you cannot also say it's because of the multiple bonds. Are you getting it now? You cannot say it's because of the multiple bonds. Is that okay? Therefore, there is something that is actually influencing or making these compounds here to have a very high chemical shift value. Is that okay? Now, the reason is this. In the case of pi electrons, or in the case of this double bonded compound, the pi electrons circulate under the influence of the applied field. So, the pi electrons, of course, you know, for every double bond, one of the bonds is pi and the other one is what? Sigma. The pi electron, you know, when you now put your external magnetic field, you know what will happen now? We'll have a net field. Is that okay? But the pi electron circulate, this word, please take note of it, circulate under the influence of the applied field. The effect is complex and can lead to a shift to higher frequency. Is that okay? Downfield shift. We said a shift to higher frequency is what? Downfield. Now, on the other hand, you see that you call it downfield shift or paramagnetic, or a shift to lower frequency, which is upfield or diamagnetic. So these effects are anisotropic. When you say anisotropic, it means it actually in two different directions. It could influence the frequency in what? In two different directions. So what is actually responsible for this anisotropic effect is the circulation of what? The pi electrons. Of course, you know the pi electrons. We say the electrons is what is responsible for what? For the magnetic field around this. What is responsible for the magnetic field around this place here are the electrons here, right? Now, because of these pi electrons, the small magnets, listen to the small magnetic field may be high in some instance and it may be low in some instance. Are you getting it now? It may be high in some instance and it may be low in some instance because of this one circulation. So when it is high, of course, you know the net magnetic field will be what? Reduced, and that will go to lower frequency. When the magnetic field of this small magnet is actually very low, net magnetic field will be high, frequency will be what? High. No, the most important thing you should just know here is that in the case of pi electrons actually circulate under the influence of the applied field. This effect is complex and can lead to a shift to high frequency or low frequency. And anisotropic means it's pointing in two different directions. Is that okay? So that is the general idea on anisotropic effect. So for the anisotropic effect, it depends entirely on where the proton actually work, on where the pi electron circulates. Are you getting it? It circulates in such a way that some of the protons are shielded and some are deshielded. Now, of course, you know those that are shielded, we have low chemical shift value. While those that are deshielded, we have high chemical shift value. Is that understood? So, and most times protons at the exterior like this are usually shielded. That means those ones outside here, they are deshielded rather. Deshielded. And those here are shielded. In the center are shielded. Now, most of the protons outside an aromatic ring like this are usually deshielded. While the ones inside is rare are shielded. Now, of course, you know that when something is shielded, low chemical shift value. Deshielded, high chemical shift value. Is that okay? Now, what do you want to know about anisotropic effect? It's an effect that actually have different properties of a compound when measured in different directions. Are you getting it now? Of course, we said that the pi electrons can circulate. Now, when you measure it in one direction, the protons will be deshielded. When you measure it in the other direction, they will be shielded. That's why they call it anisotropic. In such a way that when you measure them in different directions, you are having different properties generally. The ones that are deshielded, high chemical shift. The ones that are shielded, low chemical shift. Is that okay? So that's the general idea on anisotropic effect. So when they ask you what is anisotropic effect, you say anisotropic effects, these are effects of a compound that actually differ based on the direction, or these are properties of a compound that differs based on the direction of measurement of that direction of measurement of the effect. For instance, the chemical shift for protons attached to carbon-carbon in alkane is higher than could be accounted for by electronegativity effect alone. This is true for aldehyde proton, whereas alkyne appear at relatively low chemical shift. In this case, pi electrons circulate under the influence of the applied field. This circulation, it actually shields some of the proton, which we have low chemical shift value, and deshields some of the protons, which we have high chemical shift value. Is that okay? So that is why they call it anisotropic effect. Is that okay? So that is that for anisotropy. All right. I think we've done justice to that. Now let's talk about the spin-spin coupling. We don't actually have anything to do here. Now, when we are talking about protons generally, when they are represented in NMRO spectrum, the number of lines observed for a group of protons is not related to the number of protons in that group, but rather it is related to the number of protons in neighboring group. For instance, you have CH3, CH2, CH or CH2OH. What we are saying is, if you consider proton A, the number of lines you are going to see in the spectrum for this one here is not related to the number of protons you have on this carbon. Are you getting it? But it depends on the number of protons on the adjacent carbon. And there's a rule usually used to ascertain that, called the N+1 rule. So if you are drawing an NMRO spectrum Now, the number of lines you are going to see for CH3 will not be due to CH3, but rather it will be due to what? This proton here added by 1 or increased by 1. So if you want to draw the spectra or the peaks you are going to see for this CH3, you use this one here and add 1 to it. So how many protons are here? 2. So you now say 2 plus 1, which is what? 3. So for this one, you are going to see 3 peaks for A. Now, if you are considering B, now to this side for B, you have CH3, you don't have oxygen. Are you getting it? Oxygen is not a proton. This hydrogen here, you actually consider just this CH3. Now, if you consider this CH3 just adjacent to it, now, how many protons are there? 3 protons are there. Are you getting it now? So it will be 3 plus 1, which equals to what? 4. So when you are considering for this CH2, it will be the neighboring carbon, the number of protons on the neighboring carbon plus 1. And there's a way to actually draw it. All the lines will not be different. So if you have 3 lines, you are not to draw the 3 lines of equal height. If you have 4 lines, you are not to draw the 4 lines of equal height. You use what we call the Pascal triangle method to actually do that. Pascal triangle says this will be what? 1. Here will be 1, 1. Here will be what? This is becoming too wide already. Here's 1, 1. Here's 1, 2, 1. Here's 1, 3, 3, 1. Here's 1, 4, 6, 4, 1. Here's 1, 5, 10, 10, 5, 1. Here's 1, 6. Now, this is how you just do it. This 1, 1, 1, 1. Then you are now going to take 1, 1. Add this 2 here to give you, add 1 plus 1 to give you 2. Then you write 1, 1 again. Then 1 plus 2, 3. 2 plus 1, 3. Complete. Then you write 1. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. Then you complete it with what? 1. You write 1 again. 1 plus 4, 5. That's how you just be taking it. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. Then you write 1. Then this one, you write 1 again. 1 plus 5, 6. 5 plus 10 is what? 15. 10 plus 10 is what? 20. 10 plus 5 is 15. 5 plus 1 is what? 6. Once you reach this last one, you add 1 again. And that's how you are going to be doing it. Now, depend on the number here. The highest number here will have the highest peak. So for instance, if I'm drawing for 1, it will just be one straight line, right? If I'm drawing for 1, it will just be one straight line. Now, if I'm drawing for this 1 and 1, there will be 2 straight lines, but the 2 straight lines will be of equal height. All right? 2 straight lines, but they will be of equal height. If I'm drawing 1, 2, 1, you see that 2 is higher than 1 and 1. So I'm going to have one line that is very tall, and then the other 2 will be of what? Equal height. Is that okay? Then if I have 1, 3, 3, 1, it means you are going to have 2 lines will be equal, right? Good. 2 lines will be equal, and then you are going to have 1, 1. This is what we call singlet, doublet, triplet, quartet. Are you getting it? That is the name they call them. When it's 1 line, you call it a singlet. When it's 2 lines, you call it a doublet. Then this one is what? Triplet. And then this last one is what? Quartet. And then you continue. For this one, 1, 4, 6, 4, 1. Now you have 1, 4, 6, 4, 1. This will be, the 6 is higher, so it will have very long line. You have 4 and 4 equal height, so you are going to have these 2 equal height, right? And then you have 1, and lastly 1. All right? Then you have 1, 5, 10, 10, 5, 1, right? Now that will be 2 lines will be equal height, 10 and 10. So let me just look for space here to draw this. 10 and 10 will be of equal height. So we draw 10, 10 equal height. 5 and 5 will be of equal height to this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Is that okay? So this will be 1, 2, and then you are going to have 5 and 5 will be of equal height. So you have 5 and 5, and then 1 and 1 will be of equal height. Sextieth. Are you getting it now? So that is how to actually draw this for most compound. That's what we call what? The spin-spin coupling. Is that okay? Now, in our next lecture, we are going to take some practice example, having in mind different chemical shift values for different compound. All right. Thank you very much for your time. See you in the next one.